Assalamu alaikum. Good afternoon, everyone, today. I'm going to be talking about mining electrification. I'll try to keep this one short and sweet. Um, okay, so let's start by who are we, 3ME Technology. A while back, around 2014, a miner out in a farm somewhere near Sydney was not too happy with the fuel prices. So they decided to go and electrify a Mazda 2 with a hybrid. They continued to electrify smaller projects, mostly commercial on-road, and then eventually struck the attention of two mine personnel that saw that there is an immediate need for electrification in the underground mining environment in Australia. Why was that? We'll walk through that today. And basically, ever since that day up until now, it's been constant development to ensure that our mines, our construction, tunnels, and all of that has been electrified by 3ME technology in Australia. Our product development has been driven by our target markets being mining, military, and marine, and that's where the name 3ME technology comes from. The main drivers in the Australian market is similar to all drivers around the world and the pressures that we're experiencing. It's around decarbonisation, improved working condition for the underground mining environment from a safety point of view. If you were to put an EV underground, you're eliminating diesel particulate matter, which then allows us to breathe better working conditions, elimination of noise and heat, which means that you will need less ventilation cost underground, which then will lower your energy consumption and cost overall in the mine. And of course, improving the environmental impact, which is an important point. Now, the electric mine. What I've got there on the screen is a concept electric mine. The four different topics is battery electric vehicles, so the actual fleet operating in the mine. The other concept is power management. So load management, what does that actually mean when you electrify a fleet? We need to start thinking about an ecosystem. You would put a fleet of electric vehicles in a mine. You will need to manage the load, the grid, buffering, ensuring that all your energy is coming through at the same time. There's no peaks or loads anywhere on the system. Number three, you've got interoperability. What that means is that you need to actually make sure that the protocols are working together, communicating and connecting throughout. And of course, lastly, it's the green power source. You can put a fleet of electric vehicles and try to decarbonize and reduce the carbon emission. However, if you're still charging it from a diesel gen, it's still not carbon neutral quite yet. I guess the main focus, given that we are a battery company and a battery manufacturing company, I will be talking about the challenges that we experience from a battery electric vehicle point of view. We deal with lithium-ion batteries, mainly NMC chemistry, so that's nickel, magnesium, cobalt. The idea there is that we design, manufacture, assemble, test, to do all of that in-house, as well as the systems integration piece. And that's where the safety comes from. Some of the challenges that we've encountered would be around safety, scalability, and integration. What does that actually mean? The battery needs to be safe if we're going to operate it in the mines, given that it's an explosive atmosphere in most cases. And then our battery system has a racking system, as you can see there, that allows it to be scalable. The battery management system and the thermal runaway protection system and compliant hardware all comes in within the one pack. The racking system allows us to have better visual and control over the cells in there. So each rack has two cells upon each side, and what that allows us to do is have direct access to the cells to be able to isolate them in an event of a pressure or thermal runaway. Of course, this battery system meets the stringentest industry certifications and compliant. We've already got vehicles underground in Australia that have been electrified, and they meet those compliant standards there. And of course, the importance is that it needs to be a network battery as part of the full system integration. Recycling challenges. Now, these batteries that we're talking about are massive. They're not your small batteries. The average battery that we've been producing weighs about 1.7 tons, and it's lithium-ion, so it's full of chemicals and other things that need recycling. At the moment, there is a common trend in battery recycling, which is the redeployment. But what you need to do before you redeploy is you need to maximize your first life cycle. When the battery reaches 80% capacity after mobile use, it is no longer fit for mobile applications, and that's because it might not be able to sustain the load throughout the system. Therefore, what we will do is we'll take that out and then we will reassess and recertify. Given that it's a racking system, it is a super modular and sustainable design. The way we've designed it allows us to separate the chemicals or the cell itself from the mechanical structure. So you could take those blades out of the battery and re-rack it in a static storage solution system or a grid control and regulation system. And that's been a common trend within battery providers and suppliers. Now, of course, once it reaches the end of life at the second state, you will need to recycle it. Now, integration challenges. This one is actually a big topic. I've put in, I guess, the 4 different integration challenges that we've encountered, but today I'll mostly be covering battery chemistry and battery size fit for applications. The battery that we've designed is chemistry agnostic from a lithium-ion point of view. So you can go with nickel, magnesium, cobalt, or you can go with lithium titanate or LFP. And basically, the choice of such chemistries will actually be based on the application for the end user. All chemistries are susceptible to fire. They all have hazards and risks, but they all can be managed differently, and they all fit different applications in that instance. And so in order for us to understand what battery we're actually going to be integrating into OEM vehicles, we're going to need to adapt a full system solution. What that entails is a duty cycle analysis, which then is about understanding the operational profile of your machine. Doesn't matter what machine it is, it could be a dump truck, it could be a front loader, an integrated tool carrier. They all will have different operational duty cycles, and that is key to understand in order for you to be able to integrate it into a vehicle. That will guide the size of the battery and the chemistry. It's also important to not sacrifice the payload. With a lot of the conversions, once you've taken out the transmission and you've put in an electric motor that is much lighter normally, and therefore you're actually underweight or slightly on par with the weight there. The next stage is prototyping and systems integration. You need to be able to prototype this in an efficient manner with all the right components on vehicle, and that's why we adapt a systems integration approach there. And then we also do the control software and hardware capability in-house. What that allows us to do is actually ensure that the safety is cohesive across all, that the power is being distributed correctly, and that the battery is being managed correctly. That then flows on to charging solutions. We have, of course, assessed charging solutions off-board and on-board. We found that it's essential to have an on-board charger for your equipment, and that's because of opportunistic charging. What that means is that if you're underground in a mine or in an open pit and you're about to do a job and you're idling outside your vehicle and you have your vehicle on, you can actually keep it charged through opportunistic charging with your on-board charger, and then you could switch that off and move on to your next task. That allows you to buffer your charging. And finally, remote monitoring and asset management for the battery. It's really important to manage the batteries in real life time. And it's important for you to understand what it's actually doing in that moment of time. And what that links with is your battery management system. And the battery management system will be able to tell you if it's pressurized, if there's temperature on it, and you'll be able to isolate it. Therefore, remote monitoring is the last step that closes the loop together. That's kind of all I had. I wanted to keep it short, and if you have any questions, I'm happy to take them. I'm in the Mindtech zone. So yeah, thank you.